Okay. Hi, everybody. In this lecture, we are going to investigate multiple nonlinear regression in detail. We are going to plot the regression curve in two-dimensional coordinates and in three-dimensional coordinates also. We shall also plot the regression surface and the contour of regression plot, or the contour plot of regression. Let us begin our work. We shall carry out this work by using one example dataset where the model function includes an exponential component and a sinusoidal component also. As usual, at first we import the required libraries. Here we imported NumPy, SumPy optimize, and the curve fit method. And we also imported matplotlib as PLT. As you see here, the model function includes two variables, x1 and x2. When they are combined, they give an array-like variable, which is shown here as capital X. The model function, as I told you, is, as you see, includes the variables x1 and x2 and includes the arguments a, b, c, d. The model function then becomes as a multiplied by np exponent of b multiplied by x1. This is the first variable, plus c multiplied by np sine d multiplied by x2. So the character, as you see here, is nonlinear. The trend of the function here will be nonlinear as expected. And accordingly, of course, the synthetic data set which we are going to create will have a similar character. Because we are going to generate data sets by using random function, here, for the consistency and repeatability of the results when we always run the program, we call the seed method with a number 42. You may ask why number 42? Really, this is not a magic number in itself, but traditionally, this number is famous in engineering because really it has its real applications in real life. I have written for you here a reference talking about the story behind random seed with the number 42. Number 42 generally represents the refraction angle of light from the surface of water, which is the angle required to show the rainbow. Also, 42 is used as the order of an exponent of to the order minus 42, which gives you the time which is necessary to cross the diameter of the proton. Also, number 42 is expressed in a binary way as 010101. So this is a famous number in itself, and I advise you also to make use of it. Anyhow, now we can guarantee that at every time we run the program, the generated values from the random generator will be exactly the same. But of course, you can use another numbers if you want. You can use number 0 or 10 or 15, and it also will give you repeatability. Okay, so now we are going to generate x1 and x2. Here we use lens space method with the minimum value of 0 and maximum value of 5. We are going to generate 100 points, NP lens space from 0 to 5 with 100 points as x1. x2 also is generated as NP lens space from 0 to 10 with 100 points. Number of points here is necessary to be the same. If you give 50 points for x1, you have to give also 50 points for x2. I have given them number 100, so here it is also 100. If you want to see the results and print what is x1 and what is x2, here I am printing x1 and x2 to show only the first three values. So if you look as a result of what yes, why? Now it will be clear. So this is the first three values, x1 of 0 to 3, 0, 0.05, 0.1. These are the first three values of x1, and here is the other three values which are different of x2. Any random values, but as you see, it represents one-dimensional array. Okay, so we have generated x1 and x2 in numbers. Yes, and I have saved these two arrays, x1 and x2, as CSV files in the documents for future use. I have used, as you see here, the function save text, NP save text. I call the first file Samara and the other one Alien, and the values will be separated by a comma. CSV, comma, separated values. This is for future use. In the coming lecture, we shall refer to this file, these two files. Now, in order for the curve function to take in consideration the values of x1 and x2, so we have to combine x1 and x2 in a one array like called x underscore combined. So this is necessary as I told you, for the function curve fit to work. We have given values for x1 and x2. We need to give values for the model, which is expressed as you see here. And for this case, we need to give real values to the coefficients A, B, C, and D. And I have given them the values 2.5 minus 0.5, 1.8, 0.7. These are also randomly selected values and are given the variable names true A, 2.5 is given within true A, minus half true B, true C, and true D. So I have given real values for the A and B and C and D values, variables, and this will be, of course, used in order to find the Y value or the model function value. So I have written here Y data will be presented as the model function, and we pass there the X combined, which now represents both x1 and x2, the two variables, and the true variables of A and B and C. In order to give the Y data a random character, we add to this a component of values which are generated by the random function with normal distribution. This function has a mean value equal to 0, the standard deviation is 0.5, and the size is equal to x2 dot shape. The length of the shape, the value of the shape of x2. Maybe of x1, they have the same shape. So now we have the three data values, x1 and x2 and y after combination y data. It is called y data. Now, in order to begin our fitting with curve fit, we need to give this function curve fit the initial guess values. Really, it is not very strict conditions here. You can give any reasonable values for the four variables which we have, A, B, C, D. I have given these initial values 1 minus, as you see here, 0.1, 1, and 0.1. You can change them. The result will not be affected too much. Having this initial guess, it shall be passed to the curve fit function with the function itself, the model function, is passed to the curve fit, which is between two brackets, and the x combined now and y data. So y data, we know its value, how it is expressed. X combined also we have known now that it is the effect of two arrays x1 and x2. The model function is already expressed, and the initial values already are given. So everything between the brackets now is known to the curve fit, and as a result of that, the curve fit will give us the regression results. Regression results, as usual, consist of two major components: the point's optimum value. Every value has its optimum value for A and for B and for C and for D, and the also covariance matrix here, which, as I told you, is very useful for other statistical analysis and matrix analysis also. Could be used to find the R squared value of each variable, for example. Now we have POPT, we can consider POPT as 4 parts. The value which results with A, we call it fitted A, and the value which results for B, we call it fitted B, fitted C, and fitted D. So these are the values which are generated as optimal values for the initial selected values. Of course, now we can compare between the real values true A, true B, true C, and true D, and the fitted values, fitted A and fitted B and fitted C and fitted D. And this, will, of course, will give us an idea about the correctness and the fitness of the function. Anyhow, if we print the POPT here, the optimal points values, we shall get, as you see, here between two brackets, this one value, 2 and 3 and 4. These are the 4 values for our initial guess. Of course, the fitted parameters and these values are the same. So you will get only a difference in the number of digits. Here it is only with less number for simplicity. And here is the original values. So the original value 2.5. Now it is shown as 3.78. The other value, which is minus half, now it is as minus 0.65 and so on. So these are now the fitted values, and these are the original values. Of course, if you print the whole array which is predicted, it will include these values or very close to them values. We shall see this a little bit later. So as you see now, we have run the curve fit. We have obtained the fitted values for A and B and C. And now, if we have these values and we have the combined X combined, we can find the Y predict or all the values which could be predicted by the function, which is the model function. So the model function, we pass to it the X combined and all POPT. Here the asterisk means all. You can pass these components instead, and you will get the same answer. So we get the array which predicts the values, which gives the values of predictions for all the points of the plot or the curved line. We printed, I have printed Y predicted only for the first 25 values to make economy in the space. Here they are. Y predict beginning from 0 and ending by the 25th value. Of course, they are going to be 100 values, but I have, as I told you, made it 25. When we combined X values, remember, when I have read or printed X1, this is the first number, the second, the third number. Of X2, this is the first, this is the second, this is the third number. Now, if I combine them, I shall have two arrays beside each other. The first array begins, as you see here, with this brackets, And this first value, which is 0, this is 0, 0.505, this is the second value, this is the third value, and we continue up to 100. When finishing with this array, beside this array, in the X combined, will begin the other array, which begins from 0. Here you will see it. It begins. This one has finished now, closed. The other one begins with 0. The second term is 1.035. Here it is, 1035. The third one, 212, which will be here, 212, and so on. I have just exploded it, printed it for you to see how they look like when they are combined beside each other by using the combine of x1 and x2. So now we have also found the predicted points of the whole function. I have also saved this array in the documents by using save text for future use. I shall tell you about this in the coming lecture. Now, generally, we have the work almost done. What is left is to plot and to the functions, and the other important thing is to check the accuracy and correctness of the fitting function. To test the function, I have used two sklearn functions. One of them is called r² score. So I have to import it from sklearn. From sklearn, I have called the matrix, and from the matrix, we import r² score. Also, from sklearn matrix, I have imported mean squared error. What we have to do, we have only to pass to the function r² score the values of y data and y prediction. And both now are known to us. So they are going to be compared between each other in order to get an idea about how close they are to each other and how small is the error. The same thing applies for the mean squared error. We pass to this function the y data and the y predict also, and we print the r² value, and we print mean square error value in sklearn. This also, they should appear here as a result of our work. Here r² value is 0.381, and sklearn mean square error is about 1.54. Generally speaking, r² gives better indication and true values with linear regression, but in nonlinear regression, it gives an impression about the correctness of the work, but preferably to check the goodness of the work by using mean square error. Mean square error here is 1.54. The smaller the mean square error, the nearer this value to the 0, it means that the goodness of the function is very high. The r² generally is known as good and excellent when its value is about 1. Here it is far from 1, so it doesn't give really a very good result, but in any way or another, it is acceptable value and it could be considered okay. Now, let us go back and consider the drawing, the plotting of the curve in a 3-dimensional space. In order to do that, we have to create a figure object and to create an axis object. The figure width and the figure height are defined here. And the axis also, as you see here, we have passed to the axis projection equal to 3D, which means now we have created a three-dimensional coordinate system. And now, for this coordinate system, we give a title. We set the title. It is called curve fit plot. We set the X label, X1, the Y label, X2, because we have two variables, and the Z label is called Y. In order to plot, now we have to plot two plots. One of them for the original data set, which includes X1 and X2, that is the variables, and the Y data. And these variables are passed to the function scatter, not scatter plot, scatter 3D. Notice that scatter 3D and not scatter plot only. So we will have every point with 3 dimensions for every point, X1 and X2 and Y. Also, we plot now for the curve, we now plot 3D plot and pass there also X1 and X2. And for the Y data, here we need to put the values which are resulting by prediction. So this is representing the A element, the A variable, the A constant, popped of 0, multiplied by npx here from this function here, at the same beginning, our function A, this now will be popped of 0 multiplied by np exponent of B, instead of B now popped of 1 multiplied by x1 plus C, which is popped of 2, and D popped of 3. So these now are fixed in this expression, popped of 0 multiplied by npi exponent popped of 1 multiplied by x1, this is the first term, plus popped of 2, this is which is C, multiplied by np or npi sine popped of 3 multiplied by x2, and the color is given red. So we expect the color of the curve to be red. Now, if we run the program, now I will run it. And as you see, here are all the values which have been shown to you previously. Nothing I have changed. So I get the same values. This is the combined x1 and x2. These are the original true values for A, B, C, D. These are the fitted parameters or the popped or fitted values for them. This is the predicted values of Y for 25 values. This is the R squared error or scalar RMS error. What is left is to see or to have a look at the curve which results here. Here is our curve, which is in red. As you see here, we have already created a three-dimensional coordinates x1, this is x2, and the third one is the y. And these points now are the scatter 3D points, which are shown in this volume. And this line represents Y prediction, through which we can carry out prediction for any value of X and any value of Y. I hope that this is clear and understandable by you. Now we move a little bit forward also to show you how we can plot the curve fit in a two-dimensional space only. We do not show it in a three-dimensional. We have only X and we have only Y. But because we have two X's here, two variables, X1 and X2, so this result will be shown as dependent variable for X2. And also we can show it as a dependable value for X1 because we have X1 and X2. How to do that? Principally, the first steps which we have done in the previous example are going to be repeated here. So we have imported the libraries, we have defined the model function, the same model function. We have also defined the true values of the coefficients A and B and C and D. We have combined X1 and X2 into an X combined array. All this, we have created the data X1 and X2 the same. So we did not change anything in this up to this point. Now we have defined the Y data as the true value plus a random noise. The random noise here, as you see, NP random normal 0 dot, also the same term which we used in the previous example is used here. Here it is added to the true, and we get now Y data. Y data now is the true data or the true value plus the noise value. Okay, now in order to make prediction, we give initial values as we did before also, and we pass to the curve fit the model function as we did before, the X combined, and here we add Y data with the, of course, initial values which we have suggested as -1 and 1 and so on. So as a result of this work here, we get also POPT and PCO, P covariance and P optimal values. They will be exactly the same as we did before. In order to plot, the difference here generally is for plotting. So we created a figure, PLT figure with the height and the width 10 to with 6. And now we use PLT scatter. We did not use PLT scatter 3D. PLT scatter plot, where we passed a variable X2, not X combined, X2, we can here put, instead of X2, X1, now I'll show you X1, now X2, Y data, with a given label and a given alpha. And this is the original scatter plot. And now we will plot the curve, PLT plot also for the variable X2. And now we give the model function with the combined now, because we need the model to show or to include both variables X1 and X2. So model function of X combined, and here also asterisk popped or we can say fitted A, comma, fitted B, fitted C, and fitted D, instead of this shortened form. This shortened form is more elegant, but I have written here for you also that we can use the following line, this line, instead of this line, and it will give the same result. What is different here is instead of asterisk popped, we use fitted coefficient A, fitted B, fitted C, and fitted D. But the X combined must be included. So now we are expecting to have a plot where the X axis is given as X2 and the plot itself, which is the regression plot, which is the dependent output on the X combined array. If we have a look at it, as you see, we shall see it's the same character because it is an exponent. You see that it is now going down and down, and this character is somehow oscillatory because of the sign component, so it reflects the really model function. And as you see, this is the scatter plot of the original data set, and this is the result of regression. Of course, we can write here instead of x2, x1, and x1, and we shall get, and of course the label will be x1. If we can write here, we take it away and write x1, and here x1, and here it is already written x1. Plot x1 here. So I think we shall get a new plot, but with indication that the axes here are x1. Here it is x1, and as you see, because they have different values, here if you go up and see x1, when it is generated between 0 and 5, x2, it is between 0 and 10, so they are different with their range. So as you see, the curve somehow is different. Here is the curve representing x1 as the independent variable, and this is the regression curve, which is resulting as a result of our work. Of course, as you see, in general, with multiple regression, we can do always the same. Consider the relationship, the dependency between the independent variable, one independent variable, and the resulting curve. Or we can do that taking into consideration both variables, x1 and x2. In order to take both x1 and x2, we have seen in the previous example that this happens, and we can see really the output y predicted as a result of combination of x1 and x2. Sorry, here it is. Here is x1, and here is x2, and here is the result or the predicted curve. Instead of having this configuration as we did before, we can also do the same by plotting x1 and x2 as independent variables and calculating the third variable, which is the predicted values and plot them as a surface. Now we are talking about a surface regression or regression surface. So you give x the value of x1, you will get the value of x2, and you can define the point and how the point, how it is close or far away from the regression surface. This example here also is solved to show you that. So we have created the model function, the same model function I have used to give you an idea about the results, how they are. I have generated the synthetic data X and Y. Here they are called X data and Y data. The only difference here, when you want to plot a surface, you need to make use of the function of the NumPy mesh grid function. This array is one-dimensional array. X data is one-dimensional array. Y data is one-dimensional array. Z true, it is the same function which we have before seen. 2.5, I have given the value of A multiplied by NP exponent minus so on. So this is the Y value, which is given here as Z. This is the true value. And also you can add to this Z true, you can add the noise component to have a real Z value. This represents the original scatter plot of the graph or of the plot, which we will be compared with the surface itself. And now, in order to carry out the regression process, we need to combine x1 and x2. Here, x1 is given as x data, x2 is given as y data. So x1 and x2 are passed through the NumPy vertical stack function, which gives you the combined effect of both variables, of both arrays. It is called xy data. So xy data is the analog to x combined. Here, instead of x1 and x2, we have written x data and y data, and they are combined together through the NumPy vertical stack function. So this is necessary always because this array will be passed to the regression curve fit function. So this is the curve fit function. We have to pass through it the xy data. We have to pass the function itself and the z data as which is here with the noise. And the output also we shall get, as we have got before, the popped and PCOV or P covariance variable. This is the matrix of covariance. And now, having the X data and the Y data, we should use them to create the mesh grid for the plotting surface or for plotting the surface. So at first, we need to define the range of the values. The range here is the minimum value of X data and the maximum value of X data. The number of points is 50. We create an array now, which is called X surface. So X surface, this is an array with values between minimum of X data, which is 0 in our case, and the maximum value, which was 5 in our case. The same thing we do with the Y surface value, which is also given between the minimum value of the Y data and the maximum value of Y data with the same number of points. Now we have the range and the values of X, which is necessary to plot the surface and the Y surface. These two arrays will be, these are one-dimensional arrays, must be converted to two-dimensional arrays as it is required to plot the surface. So now we use NumPy mesh grid and pass there the X surface and the Y surface one-dimensional arrays, and as a result we get X capital and Y capital, which each of them is a two-dimensional array now. Okay, as we have these values and as we know the optimal values popped, so we can pass X and Y and popped to the nonlinear function, and as a result we get the Y, or here it is denoted as Z because we used Y symbol, so it is given as Z, which is the height of the three-dimensional plot. So now we know X surface, Y surface, and Z surface. What else we need to do? We need now to plot the scatter plot of the data set, usual scatter. We pass there the X data and the Y data and the Z data. We give it a color blue, and here we have these dots, the dots which are scattered in this three-dimensional space. And now, in addition to this, we need to plot the surface. So we call from AX here is already established and the figure already established as usual. From AX we call the plot surface, and we pass there the X and Y and Z capital. This will create the surface itself, and here we gave it a color map hot. Of course, you can use color map as Viridis or as Plasma or hot, any of them. I have given here the color map as hot. And if you run the program now, in addition to this, you will see in the program a color bar. I have plotted a color bar to be around or beside the plot. And now we shall see something like this. To be sure, I will run it again in front of you. And now, no, this is not the curve. The function, maybe it is this one. This one. Yes. Here it is. And as you see here also, the effect of the sine component is shown here, and this is the surface which results and is called the regression surface. Let me tell you one thing. You see that here is a point in blue point. These are the scatter plot, the original. The surface here just shows you the trend, the path, the orientation, which is called the optimal orientation around which the scatter plot resides. Of course, the closer the points of the scatter plot to this plane, to this surface here, not plane, the better the regression done by the curve fit. Of course, we can evaluate this always also by using the scalar criteria. I didn't do that here. It seems to me, no, we did not do that here, but we can do it the same, and it will give us an idea here, because we know why Z predict and Z itself, but there is no need for that because it is the same idea, the same data set there. So I didn't make any comparison between the results. The same results will be. This is the third part of our lecture. The fourth part of our lecture here, really it is some kind of repetition. I have used the same data set and I have plotted the scatter plot and I have plotted the curve fit function. This is the, but for x1 and x2 at the same time to show them both in one graph. Previously, you remember, I have showed only for x2, then I substituted it by x1. Now, both of them are shown at the same moment of time for clarity, not more. But you can see that the character is the same, but because they have different range, here, for example, for x1 equal to 2.5, or it reaches the zero level here about 5, x1 equal to 5. Here for x2, it reaches the zero level about 30, for example. So they have different influence on the curve, but the character of the curve is the same as before. It is somehow exponential with a wavy component as a result of the sine wave. The details of this are given also here, and they are exactly as I have mentioned before. I will not go through it. I will leave it for you to go through it slowly and to practice yourself if you find it necessary. The last important thing here also I wanted to show you is the contour plot of the regression function. As we plotted the surface, and it is called the regression surface, we can do or get the same information without plotting in 3 dimensions, without plotting the surface, by plotting the contours as shown here of regression. Each contour, as usual, represents equal values of Z, and here I have plotted beside it the bar, the color bar, with also the number equal to the number of levels which we have here. The number of levels is given, I think I remember 10. 1, 2, 3, 4, 5, 7, 8. No, let us see. Let us see how much they are. 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 9. So the ninth is here. It is some of the ninth is shown there. So here you will have about 9 sections. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 sections, and each section has its limits or values of the Z values. So here it is scaled as Z values. But also, when writing the program, I have included a statement here, the levels, and I gave suggested levels beginning from .4 to 6.8, and these levels now are included here because levels are included here, levels equal to levels. When you plot the contour by calling contour function from the PLT, you pass there the X, Y, Z two-dimensional arrays and decide what are the levels, the number of levels you need. If you do not want the levels to be given and written on the plot, you can just here write levels equal 7 or 5 or 10 or 20, and you will see the levels without having their values. I have managed to fix the value of Z on each of these plots. This is 1.2, this is 2, this is 2.8, this is 5.2. It seems to me that it is more efficient, but also instead of plotting the plots, the contour as here, you can plot the contour to be filled by adding or plotting contour F. Instead plot contour, you write here contour F, and now if you run the program, here is the filled contour plot, but numbers are not shown here. You can define the number or the Z value of the plane by using the Z value on the color bar here. This color, as you see, this curve has these values between 0.4 to 1.2, for example. This color is here. The higher value, 6.8, is for this contour here, and so on. But it seems it depends what do you want, but we can keep it. There is no problem with it. Also, at the same time here, I have plotted really the contour plot and the surface plot. And let me show you one thing here. If you, I am working with Notebook. With Notebook, if you, at the beginning of the cell, you print the wild character matplotlib notebook, you can rotate the three-dimensional plot as you wish by using the mouse. So the mouse here now, I rotate it. Yes, you see this is the surface now, and this is the scatter plot, and each point, of course, of the scatter plot, how far it is or how near it is to the plot expresses the degree of goodness of the function. Of course, we cannot do that for every point. What we can do, we do that for the whole plot. So we need to use the scalar functions in order to decide the goodness or the accuracy of the curve fit function. We have done this before also. I did not repeat this work so as to make economy of time. So what we have done, as you see in this lecture, we have considered a common general nonlinear function, and we have also created a data set with some noise so that we can compare the generated curve or the generated contour or the generated surface to compare the position of these three different outputs with the scatter plot at the original, which is the original position of all the points. And of course, we have to make use of the scalar. Let me tell you for example, here when we have done the regression by using the curve fit, it generates the POPT. The original values are, as you remember, 2.5, where they are 2.5 minus half, 2.5.7. Here they are given as an fitted values, 2.5 minus 0.5 minus 0.1. These are the fitted values for those four values which are given. Before they give you also an indication about the success of the work and to which degree they are close or far away from the real values in the scatter plot. Okay, now we have only discussed the curve fit function with the curve fit function in detail. In the coming lecture, I want to make use of some of the generated arrays so that I can show you the surface plot or the contour plot of regression by using LabVIEW. So as we did in this lecture, everything with Python, in the coming lecture, we shall do the same thing by using LabVIEW. And we shall compare the results, of course. And for the sake of clarity, I shall use the same noise component and the same function, nonlinear function, or which is used in these three different examples or four different examples. Okay, with this, I finish this lecture. I hope to see you in the coming lecture. Goodbye.